Good evening. How's everybody?
Professor, how are you today?
I am fine. How are you?
I'm good. Thank you for asking.
Okay, so for those of you who are showing up on time, can you guys see the screen that looks like a big concrete thing?
Yeah, we can see it.
Okay, great. So this is how I spent my day today. Not that you guys are too particularly concerned about how I spent my day, but I thought I would share this. This is how I spent my day. Uh, and there it goes.
So what exactly are we looking at in this video?
Are you testing it?
Yes, we're looking at carnage and wreckage. So yeah, this was testing that we're doing at our fabrication facility up in Adelanto, which on the first day of July is about 103, but it was worth it. So what you're looking at is we were testing a shear friction connection. This is a type of reinforced concrete connection where the loads in one member, as I'm pointing to, are transmitted to another member via shear right along this plane right here. And I know we just had a lecture where I know I just said you never actually fail anything in concrete through shear. Well, this is an exception. This is actually a pure shear failure surface. So what we're doing is the bottom is supported by a frame. The top has this loading plate here, and I've got a ram above that pushing down on the top. This L-shaped piece of concrete was made from a lower grade concrete that was cast up against the lower L shape, which was higher strength concrete that was cast a few weeks before. So this is hardened concrete. This was wet concrete poured up against it. And then we let the two cure for a couple of weeks, and then we tested them, and we started testing them this morning. So what we're testing for is this interface. We have like a proprietary pattern that we're using for this interface roughness. And we're also testing these dowels that we have that are stapling the two halves together. So I've got strain gauges on the steel. I've got these displacement gauges to measure the crack width and the displacement of the whole body. And I've got pressure gauges on my RAM, so I know at any given time what the applied loading is. So for those who joined just a little late, I'll do it one more time. It's just a few seconds, but keep your eye right there in the middle. That had something like 40, 50,000 pounds on it when it let go right there. So that's what I did today. Get out of there. See, once in a while, we get to do fun things.
So
Okay.
it looks like it slips.
Yeah. That's what happens in shear friction. The two surfaces slide past one another, and you provide a roughness either by roughening the concrete or providing a pattern that provides a roughness, and that roughness forces one body to kind of lift up as it's trying to slide past the other body. And as it lifts up, it puts those rebars into tension. And those rebars in tension is what clamps the whole thing together and resists the load. But sooner or later, you keep adding load to it, and inevitably, something will start slipping past the other until something really just fails. And just before what I showed you, just before those things snapped and broke and separated, the displacement between the two was something on the order of about a half an inch. So it had already slipped about a half an inch before they popped. Okay, before we start tonight, we have a full session for tonight. So before we get started tonight, does anybody have any questions that you would like to ask about anything that we've covered up till now? Anything at all? All right. So let us begin. So tonight's lecture is, we're really shifting gears now, and we're going to talk about cracking and deflection. And cracking and deflection is a serviceability issue. So everything we've been talking about up until now was strength design. Everything we've been talking about up until now was trying to determine what the loading effect is, whether it's moment or shear, and trying to determine what the capacity of the beam is, whether it's VM in or V in, moment or shear. Now, what we're talking about is serviceability. And serviceability is fundamentally different than strength design, because now we're looking at not failure mechanisms, but too much cracking or too much deflection, which again are serviceability. Cracking does not cause a failure of the building. Too much deflection is not a definition of a failure of the building, but too much cracking and or too much deflection does adversely affect the aesthetic quality of the building, or the confidence in the building, or the resale value of the building. You know, all these subjective things. If you walk into a concrete building and say like you walk into your classroom and you see cracks everywhere and little chunks of concrete falling down, and everybody's desks are rolling towards the center of the room because the whole floor is deflected by a couple of inches, you're not going to have a lot of confidence, are you? You're going to say, can we meet outside? Can we meet someplace else? Right? So it is a very important topic that we, the designers, have to address, but it's not a strength-based, it's serviceability-based. So the other thing that you must know is this whole section, we will not be dealing with factored loads. That's very important. We do not deal with factored loads when considering cracking and deflection. We deal with service loads, or basically real loads. They have no factors on them, okay? Now, everything I just said, I probably typed out, so let's see. Nope, something different. Okay. Remember, way back when, lecture 2, we learned about the cracking moment, MCR, and the modulus of rupture, F sub R. Okay, this was from our second lecture. And remember that we calculated that MCR is equal to the negative of the modulus of rupture times the gross moment of inertia divided by the distance to the neutral axis, or the center of gravity, y sub t. And the modulus of rupture is calculated as minus 7.5 lambda square root F prime C. We also learned how to find the cracked moment of inertia, I cracked, or ICR. Today, we're going to look at how to apply these ideas to find the instantaneous deflections of concrete beams. So this is our first topic, our first goal is to calculate the deflections of concrete beams. And again, under loads that we really expect the building to see. there's no point in calculating deflections under a factored load because the beam is about to fail under the factored load. That is really kind of meaningless. Like, oh, the beam's going to deflect 8 inches just before it fails. That's not really helpful. But if you say the beam's going to deflect 1 inch with the load, with the building the way that we built it, and with all of you sitting in it, and it's going to deflect 1 inch, that's a lot more meaningful. Okay. Concrete beams may start life as uncracked, but as construction is completed and the full dead load is applied, cracking will occur. So, this cracking will decrease the stiffness of the beam and deflections under the dead load effects will be amplified. So in other words, if this beam were put into service with all the load on it and it didn't crack at all, then the moment of inertia of this beam would be a lot stiffer. But it is almost always the case that the beam will crack under the loads you would expect in a real building. And because the beam cracks, its global stiffness will be reduced, so the deflections will be increased because of the cracking. When a live load is applied, the cracking will progress outward towards the ends of the beams as the moment diagram is increased with increasing load. So the difference between dead load cracking and live load cracking. The cracks don't get closer together, they just progress higher up and you get more of them out towards the end of the beam. When the live load is applied, I already said that, okay. Cracking and other serviceability issues are always evaluated with service loads, not factored loads. WDL and WLL are used instead of WU. So cracking extends to where the applied moment equals the cracking moment MCR. So if this is the level of the cracking moment, and this is your moment diagram due to dead load. So MDL means that this is your moment diagram due to dead load. Where the applied moment exceeds the cracking moment, that's where you expect to find the cracks. This illustration shows the extent of cracking under dead load only. And now this illustration, this is not literal, but what this is illustrating is kind of how the beam reacts to the load and to the cracking. So from the end to this point here, and from this point here to the end, the beam is uncracked. So you have basically the full gross section of the beam. At the midspan, it is most fully cracked, and so you have something pretty close to the cracked moment of inertia at the middle of the beam. And then you have this kind of transition between I grossed and I crack as you go from points of barely cracking to fully cracked. Okay, so when the beam cracks, the physical shape of the beam acts like some of the concrete is missing, thus reducing the stiffness. So I'm not saying the beam actually looks like this. I'm just saying that from a section property point of view, it kind of acts like this. The beam can be thought of as a shape similar to above, where at the maximum moment, the moment of inertia is very close to I cracked, and in the uncracked regions, the beam still retains its full section I gross or IG. Okay, now if I apply the dead load and the live load together, notice that the moment that exceeds M cracked is now further out to the end of the beam. So it was here that the moment exceeded M cracked. Now we're out to here. So the cracks have spread out over a larger region, which means that the beam itself feels like more of the section has been removed from the beam in terms of its effective stiffness. The spacing in the cracks remains pretty stable. New cracks do not appear between existing cracks, but the cracks will get wider. So the more load you put on here, the wider or bigger these cracks get. But the cracks basically stabilize into a pattern where you keep applying more load. You don't get more cracks, you just get wider cracks. And the apparent stiffness of the whole beam diminishes as the load increases. So from this slide, this is kind of what the beam feels like under dead load only, to this slide is how the beam reacts under dead load and live load together. More of the section has been removed in terms of how the beam behaves. Okay, any questions on this concept so far? Is this reading for you guys, what I'm trying to illustrate with this shape here?
Yes, sir.
Okay. All right, so let's keep moving. If we plot a graph of the maximum moment and the midspan deflection, so maximum moment is in the vertical axis, and the deflection at midspan of the beam, or the maximum deflection of the beam, is plotted on the horizontal axis, then if I apply, well, when I first start adding moment to the beam, m sub a, we get some deflection, delta a, and it's pretty linear, as you can see. The code uses m sub a in a very generic sense. Basically, it says, this is the moment applied at a certain stage of construction. So m sub a could be just the dead load. M sub a could be just the self-weight of the beam. M sub a could be the dead load plus the live load. See what I'm saying? It's just a placeholder for some specific stage in the life of the beam. So MA is just a maximum moment applied at the stage in question, as I said. M sub A will increase as the load stages progress. At first, the moment deflection curve is linear, as the beam has not yet cracked. So before the beam cracks, it acts like a linear elastic material. And so this is a straight line. And the slope of that line, the slope of this curve, is the stiffness of the beam. At this stage, the beam stiffness is I gross times the moment, or modulus of elasticity for the concrete. So IGEC is the stiffness of a beam. I just represents the stiffness due to section property, and E represents stiffness due to material property. So we separate the two because they are completely independent. You can use any material in any shape. So we have two terms there. But IG is the gross moment inertia, and E is the modulus elasticity. Now, as the loading increases, the beam will start cracking. Once the beam cracks, the moment of inertia will abruptly change. This causes the moment deflection curve line to flatten out. So once I got a moment higher than the cracking moment, then the slope of this line flattened. It dropped. Because once the beam starts cracking, it's not as stiff as it was before it started cracking. So you have this bilinear relationship. The slope of the first line, as noted, was the gross moment of inertia times modulus. The slope of the second line segment is the cracked moment of inertia times the modulus. As you can see, we have two apparent stiffness values, one prior to and one post cracking. Having a bilinear relationship between moment and deflection is not too useful for design purposes. It would be better to use one effective moment of inertia that would get us to the same end point. That's what the code is going to do. So instead of we go up this path and then down this path, instead of that, we're going to just figure out what an effective moment of inertia is times the modulus, and we're just going to shortcut with this path. It is inaccurate for any step along the way, but it is perfectly accurate for the end result to find the deflection A at a given moment A, right? So if all I want is this is my given moment, I want the deflection, then this effective moment of inertia gets me there. If I want something down here someplace, well, then I need to have a different effective moment of inertia. We can introduce the concept of an effective moment of inertia. From from the same moment, MA, will get you the same deflection, delta A. So in other words, instead of following a complicated path, we're going to take a shortcut and use a simple path. As the moment is increased, the effective moment of inertia will need to be recalculated. And so I sub E is dependent on the magnitude of the moment A. So we were here, right? And then when we go to here, this is a different line, and this line has a different slope. So to get to this moment from the previous moment, I need a different effective moment of inertia. In fact, every step along the way that we care to find the deflection for requires a new effective moment of inertia. As the moment is increased, the effective moment of inertia, i.e., will need to be recalculated. And so I thought I just read that. Okay, and then take it to an extreme. As the moment is increased, eventually the reinforcing steel will start to yield and will cause a moment deflection curve as shown. So this is linear uncracked, this is cracked, and then once the rebar starts to yield, it will freely deform without any increase in load. And so you can see the concept of the effective moment of inertia will still get you to the same end point if we had a way to calculate what that effective moment of inertia is. The final stage is for illustration only. No valid design will allow beams to yield under service load. So you're never going to actually evaluate this because you would be absolutely nuts to have a beam designed to yield with your service loads. Beams don't yield until you get to your factored loads. For the effective moment of inertia, we're going to look to ACI 318, section 24235, and equation 24235A, which was otherwise known as the Branson equation. And this is what it looks like. So there was a fellow named Branson, I think he was in the 60s, and he came up with this concept of, instead of asking all us engineers to calculate all these different multilinear paths, why don't we come up with an effective moment of inertia that does a pretty good job? And so he tested a bunch of beams and figured out, what was their deflection due to load before cracking and their deflection due to load after cracking, and played around with this equation until he got something that basically empirically did a pretty good job of predicting the loss of stiffness due to cracking. Okay, so this is the Branson equation. What we have here is the cracking moment divided by the applied moment. And again, this is depending on what stage we're looking at. And I'll have some examples illustrating this. But the cracking moment divided by the applied moment to the third times the gross, plus 1 minus the cracking moment divided by the applied moment to the third times cracked moment of inertia, where M cracked is equal to minus the modulus of rupture, the gross moment of inertia over y sub t, and the modulus of rupture is minus 7.5 lambda square root f prime c. MA is the maximum moment at a load stage in question. ACI 318, section 24237, states that the effective moment of inertia may be used for the deflection of simple and cantilever beams. So this equation can be used for simple spans in cantilever beams. If you have a continuous beam, you have fixity at each end of the beam, or the beam is continuous over many spans, then ACI section 24236 prescribes that for continuous beams, the effective moment of inertia shall be taken as the average of the values found by equation 24235A, that's the Branson equation, for the controlling positive and negative moment regions. The Branson equation with the cubic functions was found to match the deflection data best with the nonlinear shape as shown here. Okay, any questions? Okay, so let's do example number 1. Given we have 4,000 PSI normal weight concrete, we have 60 grade rebar, we have 6 number 8s as our flexural reinforcement. The dead load is 1 kip per lineal foot, and these are the section properties here. Let me pause here for a second, just for a second. I got a lot of questions and some confusion as to this whole concept of beam self-weight. And I used to teach this class where I would always say the dead load does not include the beam self-weight, and have the students calculate the self-weight of the beam itself. And what I found over the years is that just created more confusion. I'm already throwing so many concepts at you, especially in the summer course where we're accelerated. It's a lot of information. And I fully acknowledge that it's a lot of information. So having students calculate the self-weight of the beams, I came to the conclusion was just one of those things that doesn't really add much to the understanding for the student and just creates some confusion. So I decided a few semesters ago that I'm going to take out that self-weight thing. Basically, what I'm saying is when I tell you what the dead load is, WD is 1 kip per lineal foot, that already includes the self-weight. It also includes any slabs that are going into this beam. It also includes flooring and sprinklers and lighting and partitions and glazing and anything else that's permanently attached to this building. I didn't see why calculating the self-weight was really any different than the job we all have to do anyway of calculating pipelines and flooring and all those other things I mentioned. So again, I found it more confusing than helpful. So unless I say otherwise, usually when I tell you what the dead load is, that includes the weight of the beam. You don't have to add that to what I've done, okay? Now, if I do something different, then what I would say is the dead load does not include self-weight, in which case you would have to calculate what the self-weight is and add that in there. But for the most part, I've tried to make it where the total dead load, including the beam, is what I give you here. I was asked about this during office hour because apparently the textbook is pretty consistent in doing it the other way, where the textbook always makes you figure out what the self-weight of the beam is. Again, just my opinion, just my judgment, but there's already enough stuff to figure out. We don't need to add that to it. Okay, so that's my story, and I'm sticking to it. So if you do not say something that says does not include self-weight or something like that, then if all you're given is the dead load, you may consider that the self-weight of the beam is already wrapped up in that package. Is that clear? Does that make sense? Any questions on that?
do have a question. Okay, so with the self weight of it, how would you acknowledge that we're calculating with the self weight?
I don't see that it really matters that you're calculating with the self weight. If the self weight is included in this 1 kip per foot, it doesn't make any difference.
No, well, basically what I'm asking is like, will we run into a problem where we're not considering the dead load, we're just considering the self weight, and then would like have to use that instead or calculate that to create the dead load?
It is possible. Yeah, I mean that scenario is possible. To calculate the self weight, you just take the dimensions of the beam and you multiply the dimensions, the area of the beam, you divide it by 144, which is inches squared per foot squared, to get to square feet. And then you multiply times 150 pounds per cubic foot, and that gives you pounds per lineal foot. So it's not terribly difficult to get the self weight, but I don't think I'm going to be asking for anything where you just use the self weight and you do not use all the other dead load.
Okay. Great.
And really in the real world, it's kind of like that too, because how do you pour concrete? Well, you have to have formwork, and the formwork has to be shored up with posts or frames or something, right? And then you pour all that concrete in there, and then you wait for it to cure, and then you kick out the shores. And now it's feeling its own self weight, but you got some other dead load already there. It's a valid question. Thank you for your question. But at least for the purposes of this class, we're not going to get to that granular level. We're just going to say all the dead load together at one time, and that includes the self weight.
Okay, perfect. Perfect. Thank you so much.
Okay, no problem.
Professor,
Yeah,
so for the self weight, when say we're designing, do you also need to factor down one when you're looking for the factor load?
if the self weight was not part of the dead load given, then you have to calculate what the self weight is and add it to the dead load that was given, and then you factor that number.
Ah, okay.
So, okay, let me say it another way. Hopefully this helps. Self weight of the beam is dead load. It's just one component of many components that make up the dead load. So if the dead load that you're given does not include the self weight, calculate the self weight and throw it in there, and now you have all the dead load. But self weight of a concrete beam is dead load. That's the definition of dead load.
Okay, got it.
Okay, great. All right, back to example number 1. The dead load, including the beam, is 1 kip per foot. Oh my gosh, I can't believe I just did that. Oh, this is hilarious. Okay. Well, here's an example of how I would tell you that the self weight is not included in the beam. Oh, this is great. All right. All right. Well, hey, this is how it works. All right. So here is an example where I did not include the self weight with the dead load. All right. So let's see how this pans out. The live load is 1.5 kips per lineal foot. The dead load is 1 kip per lineal foot, but that does not include the self weight, despite everything I just said in the last 15 minutes. The span of the beam, in and out of the page, the span of the beam is 36 feet, 0 inches, and it is assumed to be simply supported for this problem. Required. What I want to know is what is the deflection for just the dead load, and what is the deflection for the dead load plus the live load. Okay, so those are the 2 load cases that I would like to know what the deflections are. One thing though is that, remember, you will never have live load on your structure without dead load. That's impossible. You can't remove all the structure and then have live load on your structure. That makes no sense. So please keep in mind that you may have just dead load, but you're never going to have just live load without dead load. They're always there together. You can calculate what the deflection is just due to the live load. That's no problem. But you never have live load in the absence of dead load. Okay? All right. Because this beam is simply supported, we're going to use the equation for deflection of a simply supported beam, which is 5 WL to the 4th over 384 EI for simply supported beams to find deflections. Okay, our solution. All right, well, in order to calculate the deflection, I need to know what the modulus is, E, and I need to know what I is, the moment of inertia. We have the loads, we have the span. So the gross moment of inertia is BH cubed over 12, or 20 times 27 to the 3rd over 12. That's the width and the height, which gives me 32,805 inches to the 4th for my gross moment of inertia. My modulus of rupture is minus 7.5 lambda square root F prime C. So I said normal weight here, so that means my lambda is 1. And my F prime C I said is 4,000, so that goes there. And I get minus 0.474 KSI. So what does that mean? That means the tensile stress in the concrete can get to minus 474 PSI, and then it is assumed that it will crack. So my cracked moment is minus the modulus rupture, gross moment of inertia over center of gravity. So I plug in minus 0.474 KSI, 32,805, and center of gravity for a rectangle is halfway up, so 27 over 2 gives me 1,152 kip inch, or 96.0 kip feet. My modulus, this is normal weight concrete, so I can just use the simpler form. It's 57,000 times the square root of F prime C. So 57,000 times the square root of 4,000 is 3,605 KSI. Modulus elasticity of the steel is 29,000 KSI. And we need to find the cracked moment of inertia. We have the gross moment of inertia. We need the cracked moment of inertia. So remember when we did this and we summed the first moments about the center of gravity? First, we had to find the modular ratio, which is modulus of steel over the modulus of concrete, is 804. The area steel problem specifies 6 number 8, so 6 times 0.79 is 4.74 inches squared. And so the transformed area of steel is that times 8.04 is 38.11 inches squared. So the transformed area of steel into a like concrete material then makes this 38.11 inches squared. Then we equate the first moments. And so the first, the concrete section, the area is B times X, and then the moment arm is X over 2. So B times X over 2 times X is BX squared over 2. And that is equal to or balanced by the transformed area of steel times the distance from there to the same neutral axis, which would be, I haven't got there yet, sorry. This is 20x squared over 2. Now that's equal to the area of steel times d minus x. So the distance from the steel to the neutral axis is d minus x, which is 38.11 times 24.5 minus x. And this is a quadratic. So you collect like terms, solve for your x, and you get, first of all, take the positive root, and you get 7.94 inches. That's x right here, the distance from the top of the beam to the neutral axis. Then you can check your work by summing the distance. And I think I took everything from the bottom of the beam. So I found the distance to the neutral axis from the bottom of the beam. And I had the area of concrete is 20 times 7.94 times the total height minus 7.94 over 2, plus the area of steel times that distance is 2.5 inches divided by the total area. I get 19.06 inches from the bottom of the beam to the neutral axis. 27 minus 7.94 gives me 19.06 inches, the same. And so that tells me we did this correctly, right? So using the quadratic to find the neutral axis and then double checking that the center of gravity is also at the neutral axis tells us that we've done this correctly. So now I can,
Professor,
yes.
where are you getting the YB formula from? So I know what each number means.
The YB formula is coming from your mechanics of materials class, where it is equal to the first moment divided by the area. So a first moment is an area times a distance divided by the area. So that equation comes straight from your mechanics of materials. It's also what you would call a weighted average. So you take if you have multiple pieces, you take each piece times its centroidal distance from some reference point. So this area times the distance from the center to the bottom of the beam, plus this area times its distance to the bottom of the beam. And then you divide the whole thing by the total area. And as long as you measure everything to the same data point, then the number you get will be the center of gravity of the whole system from that data point. Okay. But yeah, go back to your, I don't know if they did it in statics. They might have done it in statics too, but certainly I know for sure it's in mechanics of materials because we just finished that up a few weeks ago. Okay, and speaking of mechanics of materials, this is your parallel axis theorem right here. How do you find the moment of inertia of something spread out over several different pieces? And that was also a mechanics of materials thing where you take the moment of inertia about its own axis here, plus the area times the distance from the centroid to the centroid of the whole section squared here. And then the moment of inertia of the steel about its own axis is ignored. It's negligible, so we just ignore that. That's why you don't see that term here. But the area times the centroidal distance squared is not insignificant. That's actually a pretty big number. So that's why you have 3 terms here. Add it all up, and you get a cracked moment of inertia of 13,788. That's just the sum of all these numbers. Okay. Any other questions about this process?
The one that you said is ignored is the height of the steel area, right? Which
Yes.
is relatively small.
Correct. If I did not ignore it, just for completeness, so you know what it is I ignored. If I had not ignored it, then you would have saw another term here that would have been 38.11 times 1 inch to the third divided by 12. See what I'm saying?
Divided by 12?
Yeah, BH cubed over 12.
Oh, okay.
Right? Yeah. But we ignore it because this isn't actually a strip that's 38.11 wide and 1 inch tall. That's just kind of a construct to kind of help picture a transformed section of concrete, but it's not really 1 inch high and 38.11 wide anyway. So what it really is little circles of steel. So it's appropriate to ignore. But again, had I not ignored it, you would have saw one more term that looked like this. That would have been 38.11 here, 1 inch to the third here, divided by 12.
Okay.
Okay. All right, we now have all the pieces to use the Branson equation to calculate what our effective moment of inertia is. We have M cracked, we have MA, I gross, M cracked, MA, I cracked. That's what all these calcs were to do, was to get those variables. Now that we have them, we can say that the dead load, and that was so funny, but here's how you calculate the self weight if it was not included in the load that I gave you. So the load I gave you is 1 kip per foot, plus you take the area of the beam, which was 20 times 27, you multiply it times 150 pounds a cubic foot, that's normal weight concrete, and you divide by 144 because you're in inches squared and this is in feet squared. And that gets you a total 1.563 kips per lineal foot. So that's your total dead load. So the moment due to dead load, because this was determined to be simply supported, the moment is WL squared over 8. So W is 1.563, L was given as 36 feet, and divided by 8, you get 253.2 kip feet. The live load moment is WL squared over 8. 1.5 times 36 squared over 8 is 243 kip feet. Okay, so first we want to look at the deflection delta due to dead load only. That was part A. So therefore, M sub A is equal to the dead load moment. Again, I want you guys to catch this concept that M sub A is just the applied moment. So the only moment applied at the first stage is just dead load. So M sub A equals 253.2 kip feet. M cracked over MA is the 96 kip feet that we found, divided by 253.2 is 0.379. If this number here, M cracked greater than MA, if that's greater than 1, then we just use 1. And the effective moment of inertia is just the gross moment of inertia. If you have an M cracked greater than MA, then this number would be bigger than 1. That doesn't make any sense. You can't have an effective moment of inertia larger than the gross moment of inertia. It can never be larger than the gross moment of inertia. That's the whole beam. So if this number comes out bigger than 1, then just use 1. Okay, now that I have my Branson equation, I plug in 0.379 here, my gross moment of inertia here, 1 minus 0.379 to the third here, and my crack moment of inertia here. And I have an effective moment of inertia of 14,823 inches to the fourth. See, so this was gross and this was cracked. Once it cracks, it loses a lot of stiffness. I mean, this is what, maybe less than half of the gross stiffness. And with the dead load moment of 253.2, our effective moment of inertia is a lot closer to our cracked moment of inertia than it is to the gross. Okay, now my deflection due to dead load is 5 WL to the fourth over 384 EI. And now I have all my tools. I can plug in W, I can plug in L. Be careful here. because almost always your load is kips per lineal foot, your span is in feet, your modulus is in kips per square inch, and your moment of inertia is inches to the fourth. This is totally and absolutely incongruent. But what you can do to fix that is multiply the whole thing by 12 to the third. Why is it not 12 to the fourth? Because this is feet to the fourth, but you're dividing by a foot over here, so you lost one. So it's actually feet to the third. So you have 12 to the third to get you from feet to inches. And once you multiply by 12 to the third, then everything in the equation is been brought to a common unit of kips and inches. And multiply this out, I get 1.105 inches of deflection, and that is down, gravity's pulling it down. And so this is my deflection due to dead load only. But this absolutely takes into account the less rigidity of the beam due to cracking. Okay, next we want the deflection of delta due to dead load and live load. So therefore, now my applied moment is both the dead load and the live load together. So I got 253.2 plus 243 equals 496.2. My M cracked over MA is 96 over 496.2 is 0.193. So my Branson equation, all the gross and the cracked are still the same. The only thing that changed was my M cracked over MA. And now I have an effective moment of inertia of 13,925. So you see how this works? Every time you move to a new moment level, you have to recalculate your effective moment of inertia. The load at this point is the dead load plus the live load, which gives me 3.063 kips per lineal foot. And so the deflection due to dead load plus live load, 5 WL to the fourth over 384 EI. I plug in my W, my span, my correction factor for inches to feet, my modulus, and my now new effective moment of inertia, and I get 2.306 inches of deflection down. So this is dead load plus live load. Live load alone cannot be directly calculated, okay? This part is really important. A lot of people miss this, so please pay attention to this part if nothing else. Live load alone cannot be directly calculated because the live load never lives in a vacuum. It's always there with the dead load. So the beam has already been cracked due to the dead load. When you apply live load, it just gets more cracked. So you cannot use the Branson equation with just the live load. It never works. You have to do it the way I did it, where I used the Branson equation with the dead load and the live load together. If you want to find the deflection just due to live load, you have to calculate the deflection due to dead plus live and then subtract the deflection due to just dead load from that to get your live load. Okay, so the delta live load cannot be found from the Branson equation. You have to use the delta D plus L minus the deflection due to D. So the 2.306 minus the 1.105 we found previously, my live load deflection is 1.201 inches. Okay, this is very important. This is the only way to get the live load is to do it exactly how I did it here. Okay, any questions on this topic?
I have a question, Professor. where this deflection's gonna be on the beam.
Midspan.
Oh, so it's always so in our case it's gonna be at 18 feet
Yes.
since our
Yes.
ln is 36.
That's correct. Uh-huh. Yeah. But this equation, which you can look up in the table, any structural book basically will have those tables. You can Google it online. You can find this equation in a table form. You can find that equation in your mechanics of materials course. But when you look up this equation, it has very specific constraints. It has to be simply supported and no point loads. It has to be a linear load, as you see here. And the definition of this equation is that it's the maximum deflection at midspan. If you wanted the deflection anywhere else, that's a different equation.
And then in this case, this is the maximum deflection
Yes.
for the dead load and live load.
Mhm.
Okay.
Yes. Absolutely. Yep. Any other questions? All right. Let's take a 10-minute break. Let's take a 9-minute break. Let's start back up at 6:05. Okie dokie. We are back. Okay, so you guys still there? Everybody still awake?
Yes.
Awesome. All right, so let's do example number 2. We are going to repeat example 1, except that now we're going to assume a fixed end support as opposed to simply supported. So we have the same given, 4,000 PSI normal weight, 60 grade, 6 number 8s. Dead load is 1 kip, not including self weight. Live load is 1.5, span 36. But now we are assumed fixed end. Required. Find the deflection delta for dead load and for dead load plus live load. So this time, instead of using 5 WL to the 4th over 384 EI, for a fixed end condition, we're going to use just WL to the 4th over 384 EI for fixed end beams to find deflections. Solution. Okay, so from example 1, we found that the crack moment or the cracked moment is 96 kip feet. I gross is 32,805. I cracked is 13,788. Sorry. Dead load is 1.563 kips per foot. Live load is 1.5 kips per foot. So first we want to find the deflection delta due to dead load only. Okay. We need the moments from both the positive and the negative bending. Let me just make sure everybody's on the same page here. If this is my beam, then when I say fixed end, that means that this beam is not simply supported on pins and rollers, but rather is rigidly attached to a column or wall or something like that. And the difference, the important difference here, is that the moment diagram will now look something like this. So you're going to have a negative moment at the ends, which puts the top of the beam in tension, and you're going to have a positive moment in the midspan, which puts the bottom of the beam in tension. Okay, so I want to make sure everybody's on the same page when I talk about fixed end support. Any questions about this? Okay. All right. So again, referring to tables, which there's all kinds of sources for tables. You can Google them. I can look in the steel manual. There's all kinds of places you can look these up. But according to tables, when you have a fixed condition for a beam, then your maximum positive moment is WL squared over 24, which in this case for dead load is 1.563 times 36 squared over 24 is 84.4 kip feet. The maximum negative moment is minus WL squared over 12. So minus 1.563 times 36 squared over 12 is minus 168.8 kip feet. ACI 318 section 24236 says for the computation of M sub A, you take the average of the dead load positive and the dead load negative. So you take the average of the maximum moments at the midspan and the end to find an average moment. So what I do is I took the positive moment plus the absolute value of the negative moment divided by 2. So 84.4 plus the absolute value of 168.8 over 2 is 126.6 kip feet. So now I can calculate my M cracked over MA is 96 over 126.6 is 0.758. So for the Branson equation, I put my 0.758 here, my 0.758 here, gross moment of inertia, cracked moment of inertia, and I get an effective moment of inertia of 22,070 inches to the fourth. Then my deflection is WL to the fourth over 384 EI. I put in my W, my L, my correction factor, modulus, and your moment of inertia, effective moment of inertia, and I get 0.148 inches down. Big difference, huge difference between a simply supported beam and a fixed end supported beam. Next, we find the deflection due to dead load and live load in the moments. So my dead load moment is 81.0 kip feet. My dead load negative moment is minus 162. These two numbers we already found. Oh, I got a typo there. Okay, that's supposed to be 84.4 there. Why is it not there? Same typo. Oh, no, that's a really bad typo. Arr. Okay, sorry guys. Bear with me while I write this down. That is slide. About 202. So lecture 9, slide 202. And 5 plus minus. Okay, I know I'm babbling to myself. The problem, the typo is right here. This is supposed to be L, M live plus M live negative. So then here it is supposed to be WL, WL. I'm calculating the live load moments because I already have the dead load moments. So the live load moment is 1.5, minus 1.5, 81, and minus 162. These are the right numbers. I just have the wrong, that D is supposed to be an L, that D is an L, that D, and that D are all L's. This is a live load calculation. So now that I have my maximum positive live load and my maximum negative live load, I plug them in down here, and my applied moment is my dead load moment, which is the 126.6, plus the average of 81 and 162. So there's my 126, my 81, my 162, and I have 248.1 kip feet. I'll stop here. Anybody have questions with the babbling and gibberish that I just did here for the last 2 minutes?
So that one's supposed to be ML positive, ML negative.
Yes. And ML positive and ML negative are based on WL and minus WL, not WD that you see.
Okay.
All right. So now for the dead load plus live load case, I do M cracked over MA is 96 over 248 is 0.387. Kind of get the flavor here. So every time that you calculate a new applied moment, you recalculate the effective moment of inertia. So I got 0.387 gross, 0.387 cracked. That gives me 14,890. And the total load is 1.563 plus 1.5 is 3.063. So the deflection, WL to the fourth over 384 EI is 3.063. The span, correction factor, modulus, and my new moment of inertia. And that gives me 0.431 inches down. My live load deflection then can be found by subtracting the dead load out of the dead load plus live load. And 0.431 minus 0.148 gives me 0.283 inches down. Okay, Any questions about that? That was all finding instantaneous deflections. Okay. All right. Now we're going to talk about something called long-term deflection. Deflections that were found in the previous section were instantaneous or happen nearly immediately after the application of load. So when we put the dead load on, that deflection that we just calculated happened immediately after the application of that dead load. When we applied the live load on top of the dead load, those deflections we just calculated happen immediately. They're instantaneous. But because of the effects of creep, instantaneous deflections will continue to grow over time if that load is sustained. Okay, remember in the first lecture we talked about creep and two effects of time and loading. The age of concrete when first loaded. So creep is greatly increased if the member is loaded early. So this is like loaded on day 1, loaded on day 4, loaded on day 7, as opposed to 2 to 3 months. This effect is not addressed by ACI. So what this is basically showing is these are multipliers. So if you loaded up a beam on day 1, then ultimately you're going to get a lot more strain than if you applied the same load 2 weeks on a concrete that's 2 weeks old. You're going to get a lot less ultimate strain than you would if you applied it earlier. Okay, so it's just kind of a general rule that the younger the concrete is when you apply the load, the more you're going to get a total deflection. The more you can wait on that concrete, then the better the building will be in terms of deflection. And the second effect of time and loading is the duration of the sustained load. If you put the load on there, how long is that load going to be on there? Many times if it's dead load, it's going to be on there the life of the building. The longer a load is sustained on the structure, the greater the creep strain will be. ACI 318 section 242413 points to table 242413 for a psi factor for different load durations. Generally, psi will be equal to 2.0 will be used for loads lasting longer than 5 years. That's what we generally use, is just twice. So basically what we're saying is whatever that deflection you calculated it to be due to dead load, in about 5 years and beyond, that deflection is going to be twice as big as it was when it was first put on the building. Sustained loads may include some of the live load. The code does not mandate this, but is left to some engineering judgment. Sustained loads may be assigned to all of the dead load. In fact, that's a given. All the dead load is always assumed to always be there. So the sustained loads will always include all the dead load, but it could include 20 to 25% of the live load for offices and residential. For warehouses, it may be 70 to 80% of the live load for warehouses, right? So if you're designing, say, a library, well, in a library, all the bookshelves and all the books on the bookshelves are considered live load. But if you're trying to minimize or figure out how much deflection you're going to get on the floor of your library, you pretty much configured that those books are pretty much always going to be there. So that's where you may want to take a larger percentage of your live load as a sustained load. Compression steel will mitigate some of the effects of creep. As the concrete creeps, the additional strain is arrested by the stiffness of the compression steel, like we mentioned when we talked about doubly reinforced beams. ACI 318, section 242411 addresses this with equation 242411, which looks like this, where psi is looked up in the table. I think this table is reproduced in the textbook, pretty sure, but it's in the code, table 242413. This is equal to 2 if the duration is 5 years or more. Rho prime was previously defined as AS prime over BWD. Remember when we did compression steel. As calculated at the midspan for simply supported and continuous beams and at the support for cantilever beams per ACI 318 section 242412. Therefore, the total deflection, delta total, is the sum of the instantaneous and long-term deflections. You got to add them all together. And in equation form, the delta total is the instantaneous deflection plus this lambda delta factor here multiplied by whatever the deflection of the sustained portion of the loading is. Okay, any questions?
So when we're designing a beam, we need to factor that one as well. Like what's gonna be the total deflection?
You mean this factor or factored loading?
No, this lambda.
This lambda, yes, yes, you do. So the example, we'll put some numbers on it, but before we get to the example, let me just give you some like broad numbers. Let's say that you analyze a beam and the dead load deflection is 1 inch. So what that means is when you pour the beam, you pour all the concrete and then you kick those shores out and the beam instantly drops because it's no longer being supported. It instantly deflects 1 inch, right? So you're the construction guy with your hard hat and you're the one knocking the shores out. And then you could go, as soon as you knocked out all those shores, you go back and you measure that beam and you'll find that it has deflected 1 inch. Then you finish your building and you open it up to occupancy. And then all your students come in and sit in the classroom that's being supported by this beam. And you go back and you measure that beam with everybody in the room using the building as intended. And maybe now you have 1.5 inches deflection, okay? So 1 inch with just dead load, 1.5 inches with dead load plus live load. And you say, all right, that's fine. I can live with that. And you pack up and you go away. 5 years later, you come back to your building and say, you know what, I'm going to measure it, just see how it's doing after 5 years. And you measure it off hours. You don't want students being alarmed with you measuring that beam and all. And so you measure the beam with nobody in the room. And now you see 5 years later that the beam has 2 inches of deflection with just the dead load, okay? And you're like, well, okay, so what happens? So you wait around and you wait for the next class and everybody fills up the next class and all the students are there. And it deflects due to the live load to another 1/2 inch again. So the total deflection would now be 2.5 inches. So let's piece it together again. The instantaneous dead load was 1 inch. The instantaneous live load was 1/2 inch. The dead load is the only portion that is sustained. So that got multiplied times 2 because of creep. So now after 5 years, the dead load is 2 inches, but the live load was not sustained. So it did not get multiplied by the creep factor. It's still 1/2 inch. So your total deflection went from 1.5 inches after opening the building to 2.5 inches after 5 years. Does that make sense?
Yeah, and that one is normal, right?
Yes, very normal. Yes.
So there's no like, let's say it deflects more. You don't need any fixing, like structural or adjusting something.
Well, now that depends. That depends. Have I ever told you the story of falling water?
No.
No.
All right. We're not going to finish this lecture today anyway. I kind of built this thing in to be kind of go over two class periods. So I think we have a little bit of time, and I think this might be instructive. Falling Water is a beautiful, beautiful house that was designed for a client by Mr. Frank Lloyd Wright, the famous architect, right? And I forget which state it's in. It's in Illinois or Wisconsin or one of those places. And the house is beautiful, but it has a little problem. When Frank Lloyd Wright designed this building, it was at a period of time in our history where an architect, if so qualified, could do the structural design of their own buildings. So Frank Lloyd Wright was of the old school, where not only would he design all the use and the aesthetic qualities and what is it going to look like, but he also designed what the structure was going to be. And he did so for Falling Water. And then the contractor, while building the building, got very concerned because Falling Water has one of its main design features is it has these balconies that are huge and they cantilever off the side of the building by 12, 16 feet or so. They're pretty long cantilevers. And they're supported, the cantilever is supported by a rock or granite foundation under the main house. And it is anchored to that rock with rebar. He's got a certain amount of reinforcement, and it's basically designed as beams cantilevering off the side of the building with negative moments like we're just talking about. But the contractor, in reviewing the drawings, became very alarmed that he didn't have nearly enough steel in those balconies, in those cantilevered beams. So the contractor brought it to Frank Lloyd Wright's attention. Are you sure this doesn't feel right? And if you know anything about Frank Lloyd Wright, he was a brilliant, wonderful architect, and he knew it, and he had an ego. And he said, don't you dare question my designs. You're paid to build it, you build it. Okay, yes, sir, right away, sir. So the contractor went to the structural engineer of record, which is kind of confusing. And I'm not sure why there was a structural engineer of record if Frank Lloyd Wright did all his own designs, but there was an engineer of record. And the contractor presented to the engineer of record that this doesn't really feel right. And the engineer of record said, oh, wow, yeah, you're right. This is like way under designed. So the engineer of record brought it up to Frank Lloyd Wright's attention that, we ran some calcs on this and this doesn't look too good. And Frank Lloyd Wright threw a hissy fit. That's a technical term. And he basically threw a fit and told the owner, you get these people off my back, you build the building the way I said to build it, or I'm going to take my ball and I'm going home. And you can just go find somebody else to design your house for you. And the owner, wait, no, don't go away, don't go away. We want your house, we want your house. We'll build it the way you said to build it. And this is all absolutely true. And so the owner told the contractor, you know what? He's really upset about this. He feels really strongly about this. Can you just build it? And the contractor's like, okay, all right, I'll build it. So you know what the contractor did? He threw a bunch of steel in there without telling anybody, like doubled or tripled the steel that Frank Lloyd Wright had. He just said, you know what, just put it in there. I don't want any problems. And so they built the building. Here's where it gets to the point of what we're talking about in this lecture. To pour the concrete balconies, of course, they had this forming system with posts and boards and frames and whatnot that went down to the ground below. And so they supported the weight of the wet concrete. And then they pulled the shores out. And then they repeated the process as two balconies overlapping, one on top of the other. So the lower one had the greater cantilever, the other one stepped back in a little bit between the two, and then about half of the lower one was encased in glass and mullions, and it became like the inside of the house. And then the other half of the cantilever was the outside of the house. If this is confusing, you can Google falling water. You'll get an image of what I'm talking about. And so upon completion of the building, they pulled the forms out. Oh, thank you, Adriel. They pulled the forms out, and the two cantilevers together dropped like 3 inches, 2 or 3 inches, something like that. Immediately, just bunk, dropped. Holy moly. And they went back to Frank Lloyd Wright and said, are you sure about this? These things are moving. This thing dropped like 3 inches. And Frank Lloyd Wright, did a little poking around. He says, yeah, you know what happened? That contractor put too much steel in there. It's weighing down my cantilevers. It was the most ridiculous response. If that contractor had not put all that extra steel in there, it would have just fallen into the creek, and falling water would have had a whole new meaning because it never would have been finished. But as it was, with the contractor throwing in all that extra steel, it did support itself, but it deflected. Then, and I forget when that was built. I guess if somebody is looking it up, maybe you could tell me, but I think it was in the 30s. Was it the 30s or the 40s? That is a long time ago. And after being in service for something like 60, 70 years, that deflection, 1939, thank you. That deflection then was closer to 6 or 7 inches after all that time. Why? Because concrete creeps. So what started as like 2.5, 3 inches is now closer to 7 inches. And it wasn't too long ago, it was a big article in Structure Magazine. Wasn't too long ago, I'm sorry, let me step back once. The clients who bought the house as their own getaway vacation house, many, many years later, donated that house to the state. Maybe if somebody has that on their Google, you can tell me which state it is. Was it Illinois? But whichever state it was, that house has since been given to the state. So it's now like a state park. Or a state historical site or something. Pennsylvania, thank you. So it's been given to the state of Pennsylvania. And now that it's owned by the state of Pennsylvania, and it's absolutely priceless because it's like the greatest masterpiece of Frank Lloyd Wright in American architecture. So it's beyond price now. But it was slowly failing after all these years. It's still failing. The deflections are still getting bigger. The cracks are still getting bigger. So I don't know, maybe 5 or 10 years ago now, the state of Pennsylvania, I guess, decided to fix it. And so they had to go in there, tear out those beams, tear out that original rebar that Frank Lloyd Wright had in there with the contractor, and they went back in and used some pretty high-tech post-tensioning methods, not to make those balconies back to zero. They never were at zero, but just to kind of bring them back 40, 50 years to where they were, closer to when they opened the building, and to keep them from continuing to grow. So that's the story of falling water. It's a story of creep and deflection. It's a story of how concrete behaves. And it's also a story of the pitfalls of a massive ego. So take that as you will.
So is that like failed architectural? Because technically the general contractor like changed the plans, and isn't that like a liability that you must follow like whatever the architects want to?
Yeah, no, yes, yes, no. Um, the contractor did not dare change the size of anything. So he didn't make the beams deeper. He didn't make them wider. He didn't change any sizing or aesthetic quality that Frank Lloyd Wright had specified. So if Frankie had the beams 5 feet deep, he kept the beams 5 feet deep. If he had them as exposed aggregate rock concrete, he kept everything. So architecturally, Frank Lloyd Wright got exactly what he asked for, except that the balcony stayed up, because if he had done it his way, they would have collapsed. They actually did a really interesting, they hired some structural engineers, modern structural engineers, in the 2000s to analyze exactly why falling water did not collapse. Nobody could figure out why it didn't collapse. It should have been down in the river. And one of the findings of that report, if I remember right, was that the mullion, the aluminum glass mullion, there to hold the glass in place, actually became a load-bearing support that helps support the upper balcony to the lower balcony. And they said without that aluminum mullion being right there, it for surely would have failed.
So it becomes a column.
Yes.
Oh, okay.
Yeah. It's just a mullion to hold the glass in place, and it became a load-bearing column. Yeah. But to your question, if a contractor had not followed the structural drawings and there was a structural failure, then it would be on him. Yeah. But that gets really convoluted if he didn't follow the structural drawings by adding more steel. It's hard to get into trouble by adding more steel. But that he didn't follow the architectural drawings, even with a letter from the engineer of record saying that the architectural drawings don't work, it's hard to blame the contractor for adding more steel. He basically saved the house. It would have been a disaster without him doing that. And old Frank Lloyd Wright would have picked up his football and went home in a big tizzy. Okay. Was that enough about Frank Lloyd Wright? And as prospective engineering students, don't let your head get swollen up too big, because it'll get you in trouble. That's the moral of the story. Okay, so where were we? We're talking about long-term deflection. Okay, so example 3, surprise, surprise, same beam, except what I did is I added a couple number 8s up here at the top, compression steel. We have the same concrete, same steel, same reinforcement at the bottom, but I added 2 number 8s at the top. I have the same dead load, not including self-weight, the same live load, same span, and this is back to simply support it. Now what's required is I want to find the long-term deflection for the beam. We've already done this problem finding instantaneous deflection, but now I want the long-term deflection. And we can assume that 20% of this live load is sustained. Solution. All right, so we got to find the gross moment of inertia. Got to find the modulus of rupture These are all repeats from example 1. We got to find the cracked moment of inertia. So I'm going through this right there. 96 kip feet is a cracked moment. The modulus is 3605, as we did before. Modulus of steel. Modular ratio is repeated. The transformed area of steel is repeated. Now, here's where we can't just keep flying along. Okay, what changed is I added compression steel. So now my A prime S is 2 number 8s, 2 times 0.79 is 1.58 inches squared. To transform it, remember for compression steel, we use 2 times the modular ratio. The 2 is because of the creep factor. -1 is because when you put that steel in there, you took out that same area of concrete. So the 2 is for creep, -1 is for the concrete that's missing, times the area of steel, and that gives me 23.83 inches squared of compression steel. So now I equate the first moments. I have bx squared over 2 plus my compression steel times x minus d prime is balanced by my transformed, I'm sorry, I haven't got there yet. This is bx squared over 2 plus a prime ast x minus d prime is 20x squared over 2 plus 23.83 x minus 2.5. And this is balanced by my tension steel times d minus x, which is 38.11 times 24.5 minus x. I take this whole long equation and consolidate it into a quadratic, solve for my quadratic, and now x is 7.34 inches. I can now find the center of gravity. I've got my concrete, my compression steel, and my tension steel component. So I now have 3 components and the total area below, and I get 19.66. 27 minus 7.34 is 19.66. These are equal, so therefore my assumption is good. And then I use the parallel axis theorem to calculate my cracked moment of inertia. I have the concrete portion about itself, the concrete portion, area times d squared, the compression steel, area times d squared, and the tension steel, area times d squared. All of that comes to 14,417 inches to the fourth. My dead load is the same as before, 1.563 kips per lineal foot. My live, I didn't do that. My dead load moment is WL squared over 8, which is 253.2 kip feet. My live load moment is WL squared over 8, which is 243 kip feet. So first we want the deflection delta due to dead load only. Therefore, my A for applied moment is just equal to the dead load moment, which is 253.2. So M cracked over MA is 96 over 253.2 is 0.379. So I then plug into the Branson equation. 0.379 to the third times my gross, 1 minus 0.379 to the third. And see, this is my new cracked moment of inertia because it includes the compression steel. So that's why this is different than the 13,000 and something that we had last time. So my effective moment of inertia is 15,418. So my instantaneous deflection is 5WL to the fourth over 384 EI, 5WL correction factor, E and I effective gives me 1.063 inches down. So this is my instantaneous deflection due to dead load only. Now we want the deflection due to dead and live load. Therefore, my applied moment is dead plus live. 253.2 plus 243 is 496. M cracked over MA is 96 over 496.2. And that is 0.193. So then my Branson equation, I get 0.193 to the third plus 1 minus 0.193 to the third. I get 14,757. Add the two loads together, I get 3.063. So my total deflection, 5WL to the fourth over 384 EI. I put in my W. I put in my new effective moment of inertia, 14,757. That gives me 2.176 inches down. So to find my live load deflection, I subtract the dead load from the dead load plus live load. That's 2.176 minus 1063 is 1.113 inches down. Okay, these are all instantaneous. So the 1.063 is instantaneous due to dead load. 2.176 is instantaneous due to dead load plus live load, leaving 1.113 due to just live load. Now we want to find our long-term deflection. So we have to calculate our lambda factor. So we start with rho prime. Rho prime is AS prime over BWD, 1.58 over 20. And I say this many times, but this is not D prime, this is D. So this is not 2.5 inches, it's 24.5 inches. Let's make sure you note that. So rho prime is 00322. So psi, according to the table, is 2 for 5 years. And lambda delta is psi over 1 plus 50 times rho prime. So 2 over 1 plus 50 times 00322 is 1.723. Okay, so what is this saying in English? If I had no compression steel, then the long-term deflection would be twice the instantaneous. But because I do have some compression steel, the long-term deflection is only 1.723 instead of 2 times the instantaneous deflection. So my delta sustained is 1.063. That was my dead load deflection, plus 20% of my live load, 1.113, is 1.286. Remember, because we were using 20% of the live load as sustained. So my total, add up everything. My total is my delta instantaneous plus my lambda delta times delta sustained, which is 2.176, which I got here for dead load and live load instantaneous, plus my lambda is 1.723 times my sustained 1.286, gives me a grand total of 4.392 inches. Is that a little shocking to anybody?
That's a lot.
Agreed. I think that's a lot. But look how it manifested itself. It's really kind of interesting. When you built the building, we, the contractor, the people who built the building, saw 1 inch of deflection. That's no big deal. And then because it was cracked and all, it, that added to that 1 inch. But then you put the live load on there, and now you're at 2 inches, 2.17. That's getting that's a little too much. But then you come back in 5 years and 2.17 has grown to 4.4, basically. So this is very important, something to be aware of as concrete design designers is this whole concept of creep. Because it takes something that might have been kind of close to begin with, and then it makes it totally unacceptable. Like that's way too much after 5 years. Okay, so there's a very important topic to understand.
So quick question, Professor. Is it like, why is it that it's rapidly growing so fast? Like, I mean, yeah, I mean, of course, like, you know, buildings are meant to fail. Like that's the design, and we kind of can't help that aspect of it. But it's like, I know that our purpose is to slow the failure process down as much as possible. What would be the reason why in this instant, like, it's not slowing down? Like that's really quick. Like how it jumped to 4 within 5 years. Like the building within fail after like 10, 15, right?
Well, not exactly. And I want to be sure we use the right terminology. This is not saying that the building is failing. It's not saying that, because the same design that got you all these deflections, you could have the same design in a beam that easily carries that load. So remember, our definition of failure is that phi min is less than mu. Well, this beam would have passed the phi min. Phi min is greater than mu. So this building can be in service for 50, 75 years, and it would never fail, in the sense that failing is that the beam's falling down, it's yielding, it's completely failing. It may never fail, but it just has a deflection that is uncomfortable.
Okay, that makes sense.
Okay, that's why this is a totally different independent check. You could have a beam that has an acceptable amount of deflection, but it fails the strength requirement. So it doesn't work. You can't do that. Or you could have a beam that totally passes the strength requirement, but has an uncomfortable level of deflection. Well, we don't want that either. See, so they're both equally important. One is a structural strength requirement, and the other is more of an aesthetic deflection requirement. And we want to check both. That's why this is part of the curriculum. You want to make sure that you understand both of the requirements. But I want to be clear about the language of fail. Failed in my mind is the beam collapsed. It's on the ground. And this is not indicating that the beam would ever be on the ground. It's just indicating that it's not architecturally acceptable. If I bought a brand new building for 20 million bucks, I don't want to see a 4-inch deflection. See, so it may have failed the aesthetic requirements, but the building hasn't actually failed. Does that make sense?
That makes sense. Yeah, no, that makes sense. Because that's what I was getting confused with. We're like, okay, we're supposed to have it at a certain like limit of like requirement, the requirement limit. But if it's past that requirement limit, and in my head, I thought it was like completely failing the building. But no, that makes sense. Yeah.
Okay, but it may be completely failing the acceptable criteria in terms of deflection, and that's absolutely true. This 4 inches did fail the acceptance criteria for deflection. I just wanted to be clear that the building isn't on the ground. It hasn't collapsed. It's just not usable because it's got too much deflection in it. But you did ask a good question. Why did it grow so much? Why did it grow so much? Well, the reason that it grew so much is because of creep. And because of these deflections are actually kind of big. 1 inch and 2 inch is kind of big to begin with. I really should not have designed a structure that would have that much deflection on day one, knowing that in 5 years, I'm going to get to something like this, right? So what would I do? Let me turn it around. How could you make this better?
Add more compressive steel.
That would help a little bit. Yes, 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 yes. So what that would do is change this number, which changes this number, which changes this number. But you are correct, but I don't think it's going to be good enough. It's not going to get you something way better than this. So what else could you do?
Change the PSI of the concrete.
Yes. Yes, yes, yes. And so what that would do is change that number right there. So if you change the PSI of the concrete, it changes the modulus of the concrete. But that's not going to get you all that far, because remember, the modulus of elasticity for concrete is a function of the square root of the strength of the concrete. So doubling the strength of the concrete only gives you like 40% more stiffness. But yes, you could do that. What else could you do?
Make it shorter.
Yes, that's a
The-
great answer.
The
Make the
length.
beam shorter. I'm slowly making my way up to there. That's where I want to be. So yes, absolutely. You could make the 36 shorter, and that would reduce the moments, that would reduce the cracking, that would reduce all of the deflections. You could also work with the architect to get more depth or more width or both. Adding more steel doesn't really do much. It's very minimal what adding steel does to the problem. Does fix it a little bit, but very, very little. But adding depth to the beam does a lot, because it changes this gross moment of inertia. And taking some of the load off, redistributing the load or reframing the building so that you're not putting so much load on that particular beam would also be a possible solution. That's what we live with every day. As structural engineers, we go, oh, I don't know. That seems like a lot of load on a really long beam that's only 27 inches deep. Well, let's see where we're at. So we would run all the way down. Do, 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 do. Somewhere down here, we would just, there. Okay, so we would run all the way down to here and say, that's not working. All right, Mr. Architect, can I go deeper? No, can't go deeper. Oh, crap. All right. Can I go wider? Well, you can go wider if you have to. Well, I have to. All right. So I can go wider. And can we get some load off of this thing? Well, see what I'm saying? It's kind of that's why they call it design. It's a design procedure until you get to a solution that is acceptable. All right. What is acceptable? How much deflection is too much deflection, and how much deflection is okie dokie? And the answer to that question, we will talk about next lecture. Any questions for tonight?
I have a quick question, Professor, for the cracking.
Uh-huh.
So I saw a video that they stretch the rebar before they put the concrete, and they say that one's avoid the cracking.
That's pre-stress.
Pre-stress, yeah.
Yeah, it's not actually
Uh,
rebar, but you can pre-stress pre-stressing rods, or most commonly you pre-stress strands.
All right, is that like, are we gonna tackle that one over here or nah?
Yeah. No.
Okay.
Not in a introduction or an undergraduate level design class. We will not. But you're absolutely right. It does exist, and it's fairly common construction practice. And as a matter of fact, it's what I do every day. We are a pre-stressed, precast fabricator. So almost everything we do in my company is pre-stressed. So yeah, that's really near and dear to my heart of what I do pretty much every day. It's also super, super common in concrete Caltrans overpass type structures. Those are all post-tensioned with a gazillion strands to achieve the spans that they do. So absolutely. And it does help with deflections. It most definitely helps with cracking. It helps with overall strength, but it is outside the scope of this class.
Okay, so that's way too far.
Yeah. But I used to teach, I haven't done it in a while, but I used to teach a pre-stressed concrete class for the graduate program. And that's where we really get into it.
Okay, thank you.
Sure. Any other questions for tonight?
Professor?
Yeah.
Is the doubly reinforced going to be on the exam?
No, it's not. Thank you for asking. I checked, I looked up my notes. The doubly reinforced beams are not in the scope of the midterm, but everything before that, including T-beams, is.
Okay, thank you.
Sure. Thank you for asking. That's a good question. Anybody else? All right, then we will close it down for tonight. Everybody have a wonderful, hopefully extended weekend. Have a wonderful 4th of July. Be safe. Don't blow your fingers off if you can help it. And we will see you here on Tuesday. Thank you.
Professor.
Thank you, Professor.
Thank you.